In the electrical industry, the terms neutral and grounded are often used interchangeably, but there's a subtle yet important difference between the two. Let's delve into these concepts, starting with the neutral conductor. The neutral conductor primarily carries the unbalanced current in a multi-wire, single-phase circuit. Think of it as the return path for the current that's not equally distributed across the phases. It's connected to the midpoint of a three-phase system, which allows for different voltage levels to be derived, or it's connected to the common connection point of multiple single-phase generators, ensuring a stable reference point for voltage. Now, let's consider the grounded conductor. A grounded conductor is intentionally connected to the earth or a conducting body that acts as an earth. The primary purpose of grounding is to provide a low resistance path to earth, which serves multiple safety functions. Firstly, it allows fault currents to safely flow back to the source, tripping circuit breakers or fuses and quickly disconnecting the faulty circuit. Secondly, it prevents dangerous voltage build-ups on equipment enclosures or other conductive surfaces, which could pose a shock hazard. In older electrical systems, the neutral conductor was often grounded at the service entrance. However, modern electrical codes, particularly the National Electrical Code, have specific requirements for how the neutral and grounding systems are connected. The National Electrical Code requires the neutral conductor to be bonded to the equipment grounding conductor at the service entrance and at all distribution panels and equipment enclosures. This bonding ensures that the neutral conductor and all exposed metal parts of the electrical system are at the same potential, minimizing the risk of electrical shock. The National Electrical Code defines grounded as a system or circuit conductor that is intentionally connected to earth through a ground connection or connections. This definition emphasizes the intentional connection to earth as the key characteristic of a grounded conductor. While the National Electrical Code doesn't explicitly define the term neutral, it does state that the neutral conductor must be grounded at the service entrance, reinforcing the importance of a connection to ground for the neutral conductor. Let's consider a few key differences between neutral and grounded conductors. Firstly, the neutral conductor carries current under normal operating conditions, specifically the imbalanced current in a circuit. In contrast, the grounded conductor typically only carries current during a fault condition, providing a path for fault current to flow back to the source. Secondly, the neutral conductor is insulated, while the grounded conductor may be bare or insulated. Thirdly, the neutral conductor is connected to the midpoint of the power source, while the grounded conductor is connected to the earth or a grounding electrode system. Now let's talk about bonding. Bonding is the process of connecting different metallic parts of an electrical system together to create an electrically conductive path. The purpose of bonding is to ensure that all metal parts are at the same potential, reducing the risk of electrical shock. The National Electrical Code requires bonding of various components, including equipment enclosures, metal raceways, and grounding electrodes. The equipment grounding conductor plays a crucial role in bonding. It connects the equipment enclosures and other metal parts to the grounding electrode system, providing a low impedance path for fault current. Now let's address the question of whether it's appropriate to use the terms neutral and grounded interchangeably. While it's common in practice, it's important to recognize the technical distinction between the two. Using the terms interchangeably can lead to confusion and potentially compromise safety. For example, incorrectly identifying the neutral conductor as the grounded conductor could result in improper wiring and increase the risk of electrical shock. Firstly, grounding provides a low impedance path for fault currents, facilitating the operation of overcurrent protection devices like circuit breakers and fuses. Without proper grounding, fault currents might not be high enough to trip these devices, leading to prolonged exposure to dangerous voltage levels. Secondly, grounding minimizes voltage differences between metallic parts of the electrical system and the earth. This reduces the risk of electric shock if a person comes into contact with an energized metal part. Thirdly, grounding helps to stabilize the voltage of the electrical system with respect to earth. This is especially important in systems that are susceptible to voltage fluctuations or surges. Furthermore, proper grounding is essential for the operation of sensitive electronic equipment. Ground loops, which can occur when multiple grounding paths exist, can introduce noise and interference into electronic circuits. A properly designed grounding system minimizes these ground loops and ensures the reliable operation of electronic equipment. The grounding electrode system is a critical component of the overall grounding system. It consists of one or more grounding electrodes that are buried in the earth or encased in concrete. The grounding electrode system provides a direct connection to earth, ensuring that the electrical system is properly grounded. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The National Electrical Code specifies the requirements for the size and installation of grounding electrodes depending on the type of electrical system and the soil conditions. The resistance of the grounding electrode system is an important factor in determining the effectiveness of the grounding system. A low-resistance grounding electrode system provides a better path for fault current to flow back to the source, improving the overall safety of the electrical system. The National Electrical Code specifies the maximum allowable resistance for grounding electrode systems. In addition to grounding, bonding is another important aspect of electrical safety. Bonding involves connecting together all metal parts of an electrical system to create an electrically conductive path. The purpose of bonding is to ensure that all metal parts are at the same potential, reducing the risk of electric shock. Bonding is typically accomplished using bonding jumpers, which are conductors that connect together different metal parts. The National Electrical Code specifies the requirements for the size and installation of bonding jumpers. The equipment grounding conductor plays a key role in bonding. It connects the equipment enclosures and other metal parts to the grounding electrode system, providing a low impedance path for fault current. The National Electrical Code requires that all equipment enclosures be properly grounded and bonded. In conclusion, while the terms neutral and grounded are often used interchangeably in practice, it's important to recognize the technical distinction between the two. The neutral conductor carries current under normal operating conditions, while the grounded conductor provides a path for fault current to flow back to the source. Proper grounding and bonding are essential for electrical safety, and the National Electrical Code provides specific requirements for these aspects of electrical systems.